Let's discuss 2026 January Chemistry Unit 6 paper. First question says, this question is about different tests used to distinguish substances. For each of the pairs of substance, give one chemical test that could be used to distinguish between them. So they have given Fe2 plus aqueous ion and Cr3 plus ion aqueous. If you take this Fe2 plus ion and Cr3 plus ion aqueous, both these solutions are green in color because chromium 3 plus ion in acidic medium is green color. Fe2 plus ion also green color. So what we can do here is, there are several things we can do. There are two things. First thing is, if you take Fe2 plus ion aqueous solution, which is a green color solution, for that we can add a base like sodium hydroxide. When you add a sodium hydroxide, what will happen? It will form green precipitate of ferrous hydroxide, and this green precipitate, when you leave it for a while, it reacts with atmospheric oxygen. You can see on the top here. It's reacting with atmospheric oxygen, forming Fe3 plus hydroxide. So this is called iron 2 hydroxide. This is iron 3 hydroxide, or we call it ferrous hydroxide and ferric hydroxide. It will oxidize into ferric hydroxide, which is a red-brown precipitate. You can see that with time, our precipitate will turn into red-brown color. So that's what we can observe when you add sodium hydroxide for Fe2 plus ion. And if you add ammonia, you can add ammonia also, this Fe2 plus ion. Ammonia acts as the same. So ammonia is also base. It will deprotonate, that means remove H plus ion from these water molecules, making it iron 2 hydroxide, which is a green precipitate. Just like in the previous case, if you leave this green precipitate for a while, it will undergo aerial oxidation, that means oxidation by atmospheric air, forming Fe3 plus. That means iron 3 hydroxide, which is a red-brown precipitate. That's what you see if you add sodium hydroxide or ammonia. You can do the same thing for chromium 3 plus ion. Now I told you chromium 3 plus ion is acidic medium, it's green color solution. But if it is a neutral medium, it will be bluish purple. You might have this doubt, why is that? The reason is, actually if you take chromium 3 plus ion stays as a coordinate complex. That means complex metal ion. So in water, what will happen? This chromium 3 plus ion gets surrounded by 6 water molecules, forming a coordinate complex. Right. But when the medium is acidic, we know that the other anions are there. Acidic medium you can't create with just by adding H plus ion. H plus ion, you have to have an anion. For an example, if I want to add HCl to make the medium acidic, instead of H plus ion, I get Cl minus ions also there. So therefore, when the acidic medium is acidic, your coordinate complex will not 100% water molecules. So instead of one water molecule, there might be a Cl minus ion acting as a ligand. So when the ligands in the coordinate complex changes, what will happen is color changes. That's why it's bluish purple in neutral medium. But in most of the time, in our laboratory condition, we will find chromium 3 plus ion green. That's why we can separate chromium 3 plus ion from Fe2 plus ion. So what we can do is, we can add sodium hydroxide. When you add sodium hydroxide, what will happen? Again, deprotonation take place. You get chromium 3 hydroxide, which is a green precipitate, same as Fe2 plus ion. But if you add excess sodium hydroxide, that green precipitate will undergo further deprotonation. That means other 3 water molecules will also lose their H plus ion. So you get CrOH6 3 minus ion. So we have chromium 3 plus ion here, and all the ligands around it is OH minus ions. This is a solution, it's not a precipitate. So usually a coordinate complex will become precipitate when it becomes neutral. You can clearly see that when they are in the precipitate form, they are charged, they don't have overall charge. But when they are in the soluble, when they are solutions, you can see they have overall charge. This is -3 because +3 in chromium 3 plus ion, 6 minuses are there, so altogether +3 - 6, it will be -3 overall charge, right? Because of that, it's a solution, it forms a green solution. So summary here is, for chromium 3 plus ion, if we add sodium hydroxide, you get the green precipitate. With excess green precipitate, you get a green solution. Or you can do this one with ammonia also. When you add ammonia for chromium 3 plus ion, first, just like in sodium hydroxide, you get the green precipitate. 3 water molecules will lose their protons. But when you add excess ammonia, if you add dilute ammonia, what will happen? Other 3 water molecules will also lose their protons and you get the green solution. Same thing what we can observe in with sodium hydroxide. But if you add concentrated ammonia, there will be a ligand exchange reaction. This ammonia can replace all these ligands, forming chromium amine complex, chromium with ammonia molecules as the ligands, which is a purple color solution. So I will go for this easy one, adding sodium hydroxide. So what are we going to write here? So we can write add sodium hydroxide in excess. So I'm going to talk about test is add sodium hydroxide aqueous solution. I can write with this symbol because you don't need to write aqueous solution because AQ is an acceptor symbol. So you can cite sodium hydroxide AQ. They know that you are talking about sodium hydroxide aqueous solution. Add sodium hydroxide aqueous solution in excess. I'll write in excess. Why I'm writing excess? There's a reason. Because both will give green precipitate, but with excess, their observations are different. What I can see with Fe2 plus ion is a green precipitate is formed. Precipitate is formed which turn brown in color with time. So it will turn brown in color with time. So if we leave it for a while, it will turn into brown. For chromium 3 plus ion, that's also a green precipitate is formed. Green precipitate is formed which will dissolve in excess sodium hydroxide. So if you add sodium hydroxide, if you keep on adding sodium hydroxide, it will dissolve there. So that's what I'm going to write for this question as the answer. Let's see. Addition of sodium hydroxide scores 1 mark. Green precipitate scores the 2nd mark for Fe2 plus ion. Chromium 3 plus ion, green precipitate that dissolves in excess. Yes, so we get full mark for this question. Right. Now let's go for next part of this question. Okay, now they are saying that, okay, we have 2 organic compounds. But I can see here, this one is a ketone. How do you know ketones? Ketones means they have carbon-oxygen double bond. Both sides of this carbon atom is attached to another carbon atom. So you can see these are carbon atoms. But here is an aldehyde. Aldehyde means you have carbon-oxygen double bond. One side is hydrogen. At least one side is hydrogen. So one is a ketone, other one is an aldehyde. Let's see how we can distinguish them. These aldehydes and ketones, they have this special property you can distinguish. Before that, we should know whether they are aldehyde and ketones. How do you know whether it's an aldehyde or ketone? It doesn't matter whether it's aldehyde or ketone. Let's take here is a ketone also. It doesn't matter what you have. When you add 2,4-DNP, or we call it Brady's reagent. So when you add Brady's reagent, what will happen here is the aldehyde react with this 2,4-DNP. 2,4-DNP means 2,4-dinitrophenyl hydrazine. So it will react with this aldehyde or ketone, gives you a yellow precipitate. So what will happen here? This oxygen atom take these two hydrogen atom, forming a water molecule, and this carbon atom join with this nitrogen atom using a double bond. That's what happens. But the mechanism is a little bit advanced. I just told you the thing which happens there in a simplest way. But this doesn't distinguish aldehyde from a ketone. So how do we distinguish aldehyde from a ketone? This is how we are going to do it. Aldehyde have this special property. What is the property? They can undergo oxidation. So if you add any oxidizing agent, that means anything which supplies oxygen atom, this oxygen atom jumps here. So that's the oxygen atom here, oxidizes it to carboxylic acid. So when you oxidize aldehyde to a carboxylic acid, what will happen? Your oxidizing agent will reduce. What is the oxidizing agent? You can use acidified potassium dichromate. What is the potassium dichromate original color? It's orange. When potassium dichromate reduce, it will become chromium 3+, and we just learned what is the color of chromium 3+, and it's turned to green. So if I add acidified potassium dichromate to aldehyde, I will see orange color will turn to green. Then next one, if I add acidified potassium permanganate, initial color acidified potassium permanganate is purple. So when the aldehyde get oxidized, acidified potassium permanganate will get reduced. So purple color will turn to Mn2+, and it's a very pale pink color. You can't identify it, so it's colorless. Right. Then copper 2+, and copper 2+, and we call it failing solution. So here failing solution, when you add failing solution, this is failing solutions. Yes, failing solution. So we call it Benedict solution. It's actually copper 2+ in the basic medium. Copper 2+ in the basic medium is blue color. So what will happen to this blue solution? When aldehyde get oxidized, this blue color copper 2+ get reduced to copper +1 oxide. So copper +1 oxide is precipitate as a solid. So what you see is a brick red precipitate. Brick red precipitate. Okay, or you can simply say it's a red precipitate. You will see a red precipitate there. Right. Then what will happen? Because no need brick red, we can put it red precipitate. Then when you add silonitrate in ammonia medium, we call it tolerance reagent. So silonitrate in ammonia medium, its color is colorless. So when you add this aldehyde, the aldehyde get oxidized, so silonitrate get reduced to silver metal. Silver metal deposit on top of a glass, you get something called silver mirror. Because silver metal deposit on the glass, it look like a mirror, so we call it silver mirror. So we have these things produced, okay, formed. Now let's see how we can use the things that we have learned here in our experiment, how to write it as a test and how to get it as an observation. But here we can see that ketones, they can't do such oxidation reaction. So since they can't get oxidized, what will happen? No observation with ketone. So if I want to identify aldehyde, first I should know whether it's an aldehyde or ketone. How I'm going to identify whether it's an aldehyde or ketone? First check whether it has this carbonyl-carbon. You add 2,4-DNP or Brady's reagent. If you get a yellow precipitate, it confirms it's either aldehyde or either ketone. Then the second test is you have to add something which distinguish aldehyde from a ketone, any oxidizing agent. I'll add failing solution. What is observation? Blue color will turn to brick red precipitate or red precipitate. And what will happen if we add tolerance reagent? It's a colorless solution. You will get silver mirror. One of them is fine. So you have test 1 and test 2. Test 1, add 2,4-DNP or Brady's reagent. Check whether it's yellow precipitate. If it is positive, then you go for the test 2, add failing solution. For ketone, the same two tests. First you add 2,4-DNP or Brady's reagent. It confirms whether it's an aldehyde or a ketone. Then you add failing solution. But since it's a ketone, it can't get oxidized, so nothing happens to our oxidizing agent, so blue color remains same. So I'll use that failing solution test to identify here. Here I'm not going to talk about 2,4-DNP. Why? For each of the pair, substance give one chemical state that could be used to distinguish. They're talking about distinguish. Help us to separate from each other. So therefore, I don't need to prove that they are either aldehyde or ketone, because they're asking, we know that they are aldehyde or ketone. Help us to separate them from aldehyde from the ketone. So what I'm going to do is, the test what I'm going to do is, I'm going to add failing solution. Okay, now can we revive, like, can we again recall what's happened with ketone? We know that when you add failing solution for ketone, nothing happens. So what will happen? The solution of failing solution color is blue. The blue color remains blue. So what we can see here is solution remains blue. But what happens in aldehyde? Aldehyde can get oxidized to carboxylic acid, so therefore failing solution, copper 2 plus and aqueous solution, will reduce to copper 1 oxide, which is a precipitate. The color of the precipitate is red. So we can write red precipitate is formed. I want to discuss this important point because when you might have noticed when I'm always talking about this brick red, I was like a little bit confused. The thing is, now if we are from any other part from Europe, when someone says brick red, this is what you get in your mind, right? This is brick red, like very dark red color. This is your brick red. I don't have my exact color, but like something like this, dark red. This is brick red you have in your mind, right? But remember, these bricks you can only find outside Europe, somewhere in Asia and Africa. Because the reason is the iron content in these bricks are very high, so therefore bricks in this area is little bit dark red color. But if you go to United Kingdom, this is brick red. Orange is their brick red because their bricks are orange. So therefore that's why I just avoiding in Edexcel papers to use the color called brick red. So therefore what I do is, if it is red precipitate, I will simply write it as red precipitate. If it is orange precipitate, I will write it as an orange one. For an example, if you take calcium 2 plus ion in flame test, what is the color? Is brick red. Brick red means orange. Remember that, right? So because we are talking about UK bricks, not anywhere else. So that's the thing here, right? So we call it red precipitate. Now let's see our answers, right? Let's see our answers for this, correct? Okay, so failing solution is the first option. Blue, okay, solution remains blue. Red precipitate is formed. Yes, that's correct. So we get full marks for this one. Okay, so what do we have here? CH3CHO aldehyde, CH3CH2CHO another aldehyde. Okay, how we can distinguish them? Both aldehydes, but there's a method. So it's called iodoform reaction. What happens in iodoform reaction is when you have a carbonyl carbon means carbon atom with a double bond oxygen and is attached to a CH3 group. When this attached to CH3 group. So what will happen when you have these type of compounds? When you add sodium hydroxide solution with iodine. So when you add sodium hydroxide solution with iodine, what will happen? This R groups comes out and form CHI3, which is a yellow color precipitate. So if you have this compound where you have carbonyl group attached to a CH3 group, the CH group will comes out forming a yellow color precipitate. That's the thing we are going to do it here. So what I'm going to do here, I'm going to add sodium hydroxide solution with iodine solution. So what I will see here is I should observe one compound will give you a yellow precipitate, other one no observation. So what we are going to write here is add iodine solution, iodine aqueous solution with sodium hydroxide aqueous solution. So I add both of them, iodine and sodium hydroxide aqueous solution. So what should I expect here is, here I can see if I draw this molecule is carbon oxygen double bond attached to hydrogen and it attached to a CH3 group directly. When you have this one, it can show the iodoform test. So I will observe yellow precipitate is formed. But what will happen here? CH3, CH2COH. It's a CH2 group which attached to that carbonyl carbon. No, to form this yellow precipitate, you need CH3, not CH2. So here, this is CH3, but here is CH2. So therefore, I won't see any observation here. So it will be no observation. Right. Now let's see the answers. So addition of sodium hydroxide and alkali. So you add sodium hydroxide with iodine solution. Yellow precipitate or yellow crystals with the first one. Second one is no observation. Okay, that's correct. So we got the full marks for that question also. Now let's go for next one. They are saying that complete the table to show how you could use low resolution proton NMR spectroscopy to distinguish between 2-methyl propan 2-ol and butan 2-ol. Right, what is this low resolution NMR? I think we discussed about IR, but I'm not going to discuss it again, because if you haven't got it, like in the last paper we discussed about IR, but I'll discuss about this NMR. We learned that from electromagnetic radiation, when you send electromagnetic radiations, different parts of the electromagnetic radiation can do different things. Let's take, that this area having high frequency and high energy. So here energy increases, frequency increases, so therefore their energy is high. So once the electromagnetic radiation with high frequency, high energy are gamma rays, X-rays and UV rays. We know what they can do. If there's an atom with an electron, this frequency can remove this electron completely away from the atom. We call it ionization. So they can ionize that much amount of power. But if you take visible light means what we can see. We'll see colors because of visible light. What they can do is, in the atom there is something called energy levels. These electrons will absorb visible light energy and they can travel between energy levels. They can go from low energy level to a higher energy level and they will again drop down. So they are just only make sure that these electrons will move in between energy levels. But if you go for infrared radiation, we discussed that it can't do even that much. What it will do is, if there is a pair of electrons shared between two atoms, this IR radiation can only make sure these electrons will vibrate. They are not moving in between energy levels. They can only vibrate because this one has less energy. And below infrared radiation, we have another wave which is even weaker than that. We call it radio waves. Now we can see that radio waves have even less energy than these two. What radio waves can do is something like this. If we take a hydrogen atom, so we have the proton in the middle which is in the nucleus, which is positive charge, and we have electrons. And if you look at this proton, it's just like a planet. It's orbit on its own axis. So it's like spinning on its own axis. So when the charged particles spin on its own axis, there might be a small tiny magnetic field is generated. So that magnetic field has a direction. If it's spinning one direction, magnetic field is one way. If it changes spinning direction, now let's take this is spinning one direction, and if it starts spinning other way around, what will happen? Magnetic field direction changes. That's what happened. To make this change, you need certain amount of energy. All right, that energy can be provided by radio waves. Radio waves are very weak. They can't do anything, but what they can do is they can make sure that this spinning of this nucleus of this proton can be changed, spinning direction. So when they do these changes, one point, magnetic field of this proton or this hydrogen atom will align with the radio waves. We know that they are electromagnetic radiation, they are magnetic field, radio wave magnetic field. So spin aligned to the external field. When a spin aligned to the external field, it has low energy. But one point, when it spin, now the magnetic field of the hydrogen atom is against the magnetic field of the radio wave. So when it spin opposed to the external field, it will have a little bit high energy. So we can see they have two different energy levels. Right, so what will happen when you send radio waves? Because of the spinning direction of this hydrogen atoms or protons changes, what will happen? There will be certain amount of energy absorbed, and we know that this type of absorption can be used to identify the amount of energy absorbed by this proton. Right, but we should also know that the different environment protons in different environment will absorb different amount of energy. So that's what we are going to do. We are going to send these radio waves. Okay, we are going to send these radio waves to this hydrogen atom, and here we keep a detector. Okay, now detector going to observe how much energy is absorbed. So let's assume first and third wave is not, but in the second one, slight amount of energy is absorbed. Then if we have a data booklet, then we refer the data booklet. Okay, if something absorbed like this, what is that hydrogen atom? In the data booklet, there's a place, okay, this hydrogen atom is close to an oxygen atom. That's why it's absorbed like that. So hydrogen atom behavior, this absorption depends on the environment of the hydrogen. Whether this hydrogen atom is attached to oxygen, whether hydrogen atom is attached to chlorine, whether hydrogen atom is attached to carbon, based on their environment. What is the atom next to it and around it? Based on that, this energy difference changes. That can be used to identify the environment of the hydrogen atom. So you can see that in this is what you can find in the data booklet. If the hydrogen atom just attached to a carbon atom, its absorption is somewhere here. If hydrogen atom is attached to a carbon which is attached to a carbonyl group, its absorption is somewhere here. You can see that if the hydrogen atom attached to benzene ring, its absorption is somewhere here. So different hydrogen atom has different energy changes to change their spinning direction. And that absorption of radio waves we can use as a reading to identify its environment. But when you look at this graph, there will be another peak at 0. That's the standard. Based to that 0 point, we design what are the environment. Because if you are going to talk about some absorption, we have to have a standard environment now. So we call it standard temperature, 25 degrees Celsius, or standard temperature is 0 degrees Celsius. Stated temperature is 25 degrees Celsius. I'll discuss that part when you're talking about energetics. But we have some standard temperature. What is the standard temperature? Standard pressure. So we have different standards. So likewise, here also I have to define something called standard. So here when we define standard environment for hydrogen, we took this molecule, tetramethylsilane. That means a silicon atom attached to 4 CH3 group. So each hydrogen atom, we assume they are in the same environment, and the absorption done by them to change their spinning direction of the hydrogen group, the proton, that's we call it standard energy absorption. That's what we call 0 here in this graph. So we call this one tetramethylsilane peak, we call it TMS peak. Right. So you have this one in the data booklet. Now we'll see how we can use this knowledge to identify a hydrogen environment or proton environment in a given molecule. For an example, this is the molecule they have given. First, we should know that how many types of hydrogens are there, because some two hydrogen atoms might have the same environment. How we are going to do it? You read it. Let's take this hydrogen atom number 1. This hydrogen atom attached to CH2 group. You can see it from this side. Okay, it's attached to CH2 group. That CH2 group attached to carbonyl group. That carbonyl group is attached to CH2 CH3 group. Okay. Let's take number 2. This hydrogen atom attached to CH2 group. That CH2 group attached to carbon oxygen double bond, and that attached to CH2 CH3 group. Then third hydrogen. This hydrogen attached to again CH2 group. That attached to carbonyl group. That attached to CH2 CH3 group. So I can see that all these three environments are same: CH2, CO, CH2, CH3. Therefore, I can assume all these three hydrogen atoms in the same environment. Same thing I can do for this other one. Then I can see that these two hydrogen atoms are in the same environment. And these three hydrogen atoms are in the same environment. So I can see that this molecule has three types of hydrogen. So three different environments. So if you have three different types of hydrogen, other than this TMS peak will obviously be there in your graph, because we add this tetramethyl silane sample into our reading when you're taking reading, because we should know where the zero appears, right? Then what will happen? If there are three different hydrogen environments, there will be three different peaks. So no need to worry about where this peak appears. That peak direction where the peak appears depends on this graph, right? We should know that. But for now, we should know that if there are three different types of hydrogen, there will be three different peaks. And the height of the peak depends on how many hydrogen you have. So this is peak C, and it's here. This is peak B, is here. This is peak A. You can see it here. Can you see that? The height ratio is peak A and C have the same height. Why? Both of them have three hydrogen in their environment. Peak B, the height ratio between peak A and C to B is 3:2. Why is that? This one has only 2 hydrogen and this one has 3 hydrogen. Surface area of the peak, or you can simply say height of the peak, represent the number of hydrogen atoms in the given environment. Alright, now we know that how many types of hydrogen you have tells you number of peaks, and the height of the peak tells you the number of hydrogen given in that environment. Now let's try to understand this question. Right, we have 2-methyl-propan-2-ol. We'll write it. 2-methyl-propan-2-ol. I'll draw it. Propan, no. So propan 1, 2, 3. Okay, 3 carbons are there. Propan means 3. 2-methyl, second carbon, there's a CH3 group. And here you have 2-ol, OH group. This is also CH3. This is also CH3. Right. Now first we'll check how many types of hydrogen we have here. Obviously this is one type. It's different from anyone else. It's attached to oxygen atom. And the second one, we'll read them. For an example, I'll take this hydrogen. This hydrogen is attached to CH2 group. That CH2 attached to a carbon atom with one side is CH3, other side is also CH3, and this side is OH. Let's take this hydrogen atom. This hydrogen atom is attached to CH2 group. That CH2 attached to a carbon atom with one side is CH3, other side also CH3, and other side is OH. Can you see? These two are the same hydrogen. So if you do the same thing for all these 9 hydrogen atoms, you will see that they are in the same environment. All these 9 hydrogen atoms are in the same environment. So that's my second environment. Right. Number of peaks, since this molecule has 2 hydrogen atoms, 2 types of hydrogen, so it will be 2. Relative peak areas. First peak has first peak has 1 proton, so it has peak areas. Other one has 9 protons. So 9 hydrogen to 1 hydrogen. So it will be 9:1 or 1:9. So anything is fine. Let's go for next one. Butane 2-ol. We'll do that one also. So it's butane means 4 carbon, 1, 2, 3, 4. 2-ol. Second carbon, there's a OH group. This is a hydrogen here. This is hydrogen here. This is hydrogen here. So we know that if they attach to the same carbon atom, they have the same environment. Okay. So I'll go one by one. This is one environment. It's a different hydrogen attached to oxygen. Then this is another environment. All these 3 hydrogen in the same environment. I think we can't find any other hydrogen in the same environment because this carbon is attached to CH, OH, CH2, CH3. So this is the second environment. Okay. This is the third environment. Okay. And this is the fourth environment. Here, this is the fourth environment. These 2 hydrogens are in a different environment. And this is the fifth environment. So we have 5 environments there. So number of peaks is 5. Relative peak area is first one has 3 hydrogens, so it will be 3 here. Then we have 1 hydrogen, 1. Then we have another 1 hydrogen, 1. Then we have 4 hydrogens. On a fourth environment, there are only 2 hydrogens. So because fourth environment, there are 2 hydrogens, is 2. Then we have 3 hydrogen in the fifth environment, so it's 3. So we have 3:1:1:2:3. Okay. Let's see the answers. Okay, we have the answers here. So we have first one, 2 peaks and 9:1. Then 5, 3:1:2:3, 3:2:1:1:3. So they say that allow the number of relative peaks in any order. So if I erase this one, because the reason is if you want to see how the peaks are appearing, we have to look at the data table. So which peak appears first. I think that's how they have done it, but you don't need to do that much work because this is only 2-mark question. So allow numbers of relative peaks area in any order. So we can see, do we have 3? Yes, we have 3 there. Do we have 2? Yes, we have 2 there. Do we have 2:1:1? Yes, we have it there. Do we have it 3? Yes, we have it there. So we have full marks for this question. So we discussed the first question of Unit 6 paper. So if you want me to discuss the other question as well, just leave a comment below. And I'll hope to, I think this Monday we will finish our examination series for this year, and I'm hoping to do you a special video to discuss what you are supposed to do after this examination, what are the areas you should study and what are the upcoming fields that there will be more job opportunities. I'm going to discuss a video on that. If you want to link about that video also, just leave a comment and keep this channel subscribed, because I'm going to discuss next 2026 June series and from IGCSE onward. Thank you very much for joining with me.